So we have login first, like it was Mr. Mike Wiesner. Paul Bergart on says, howdy, all raining here in central Kansas also. We got a giant storm ranging from Dallas, I think, going all the way out to Oklahoma and here into Arkansas and obviously
Yeah,
Kansas
we're still
as
having
well.
some audio issues with your.
Still, huh?
Yeah, it didn't sound like it before, but you're clearly reverberating again. So.
Liftoff of the mighty Delta IV Heavy rocket.
In August 2018 in Cape Canaveral, Florida, NASA launched Parker Solar Probe to touch the sun. After spending a few years spiraling closer to our star, the spacecraft has finally arrived.
It's amazing. Parker Solar Probe is touching the sun. And
This is Noor Rawafi, the project scientist of the mission. He has been waiting for this moment since the beginning of his career.
this is a dream come true. One of the major goals for the Parker Solar Probe mission is to fly through the solar corona, and we are doing that now.
So what does it mean to touch the sun? To answer that, we need to look at the sun's structure. Unlike Earth, the sun doesn't have a solid surface. It's a giant ball of hot that's held together by its own gravity. Solar material flows out from the surface, but around the sun, it's bound by the sun's gravity and magnetic field. This material forms the sun's atmosphere, the corona. Eventually, some of this hot and fast solar material escapes the pull of the sun and gushes out into space as solar wind. The boundary that marks the edge of the sun's atmosphere is known as the Alphane critical surface. We didn't know exactly where this boundary was, but for the first time in history, a spacecraft has crossed it. Parker Solar Probe ventured into the corona, touching solar material still bound to the sun. The wispy corona is too faint to see most of the time, but it's revealed during total solar eclipses. For centuries, we've been in the sun's atmosphere during eclipses because it's important for understanding how our star influences life in the solar system. But much about the corona remains a mystery.
Two of the most challenging scientific mysteries in astrophysics occur in a region that we call solar corona.
The first mystery is about the temperature. The corona is about 300 times hotter than the photosphere, the visible surface of the sun below. Secondly, there's a constant stream of particles flowing from the sun known as the solar wind. It accelerates up to millions of miles per hour out of the corona, and we don't know how. Solar wind can disrupt our satellites and technology. To better protect them, we need to go where the solar wind starts, in the corona. So heading there has been a key goal of NASA's for a while. We first proposed the idea of sending us to the sun in 1958. We didn't have the technology to withstand the journey until the 2000s. Since its launch in 2018, Parker has been heading towards our star. Then, in April 2021, during Parker's 8th orbit around the sun, the spacecraft was around 20 solar radii, or 8 million miles from the sun's surface, when it crossed into the corona.
This is a huge milestone. It took us over 6 decades to come to this point.
As Parker entered the corona, its whisper instrument took these images. Streams of plasma surrounded the spacecraft, and Parker's other instruments detected that the magnetic conditions had changed. Outside the corona, solar wind gushes out, pushing solar material away at high speeds so that it can't return back to the sun's surface. Inside the corona, the sun's magnetic field becomes stronger. Solar material is slower and tethered to the sun. Instead of a smooth divide, Parker found that the boundary between these two sides is wrinkly. These bumpy ridges are created from huge flows of plasma traveling out of the corona. Scientists are not sure why this happens, but as Parker gets closer, we're finding more clues. Before entering the corona, Parker had seen kinks in the solar wind where it would momentarily double back on itself. Scientists called these features in the solar wind switchbacks, but no one knew how or where they formed. In 2021, the spacecraft finally tracked switchbacks to one of their origins. As Parker got even closer to the sun, it detected bursts of switchbacks. Scientists traced these bursts all the way to the visible surface of the sun. Here we see distinct cells. As heat rises beneath, these convection cells churn and create funnels of magnetic energy above the surface. Scientists found that switchbacks form inside these funnels before rising into the corona and beyond. This is only one piece of the switchbacks puzzle, though. Exactly how they form is still unknown. Over the next few years, Parker will keep looking for clues as it explores our sun, the only star we can study up close. The sun is also the only star known to support life. So understanding it is critical as we search for life beyond our solar system.
That will link directly into the question, are we alone in this universe? And that is one of the biggest questions for humanity to answer.
Well, hello, everybody. I think we still have I don't know if that helps it as far as reverb goes.
No.
Maybe not. Let me try this. How does that?
Try again, say something.
Say something.
No, it's
Still okay, guys. So I'm gonna let Daniel Barth pretty much run with the program, but I did want to say hello, everybody. I'll be in chat. Some audio issues, obviously, and unless you guys can't hear it, but we think we still have a lot of reverb going on echo effects going on. We got a great audience today. Harold likes his max headroom. There we go. All right, so I'll have to go back and read a bunch of stuff, but no time to do that today. So, Daniel, I'm going to let you take it away.
Thanks, Scott. And Harold, I love the max headroom comment. I'm old enough to know what that is. Everybody else needs to go Google it up because it's hilarious. Welcome, everybody, to How Do You Know with me, Dr. Daniel Barth, and my good friend and co-host here, Scott Roberts, who shall not be named today. This is episode 38 of the How Do You Know program. And today we're talking about the Parker Solar Probe. We've been talking about the sun the last couple of episodes. We talked about the solar tsunami and the possibility that the sun could blast us with a giant coronal event. The last really big one we know about was called the Carrington event, and that was monstrous. That was an 1859 monstrous enough solar storm. It was starting fires because of electric induction through telegraph wires. But that's about the only kind of electronic technology they had back in the day. Electric lighting was still off in the future, and much less computers and all of our high tension electrical grid and satellite systems, etc. And we talked about that, and we decided we would have a program on the Parker Solar Probe. So we're going to get to that. And we're trying, as we said last time, something new with the format for the program. We're doing a few kind of news items, astronomy and space science based. The Webb Space Telescope, which we talked about a few episodes ago. The Webb Space Telescope is now fully aligned. And I'm going to go ahead and share a screen for you. You've likely seen this image, friends. This has been on the web a lot and on the internet all over the place. This is the alignment image for the Webb Solar Telescope. They've got all 18 mirror segments lined up, and they say that the alignment is even better than they had hoped. What's really interesting, you've got that one star brilliantly lit there with the diffraction spikes, very beautiful, but almost everything else in that image is a galaxy, which just knocks my socks off. This is just tremendous. They're just pointing at one star, and look, the sky is peppered with, I don't know, looks easily more than 100 galaxies in that one relatively small image. So I think Webb is just going to knock our socks off. Of course, we've talked about Webb being this really fascinating instrument that breaks down spectra and looks in the infrared and near infrared spectrum, which most telescopes do not do. Hubble does not do this. And the reason that Webb picked that infrared range is because that infrared light penetrates dust and cosmic dust that forms when stars form, and it lets us peer inside and see what forming star systems look like. It lets us peer farther back in time to more distant galaxies, both in time and space, because there's dust in space. Space is dusty, it's not empty. The other interesting thing we've talking about today, you've probably seen that the Artemis Space Launch System, the SLS, this new gigantic Saturn V style rocket that NASA has been building for more than a decade. The Artemis Space Launch System rolled out on a wet fuel test for the first time. But in our other news item, the Inspector General said that the Space Launch System may not be a sustainable launch vehicle. The launch cost for the SLS, $4 billion a pop, which means that although it has this tremendously big lift capacity, the lift cost to orbit is something like $68,000 a kilogram. And okay, you can move really big things, but it's gonna cost you big bucks. Oh my gosh. And they said that this launch cost is saying, because it's a single-use rocket. single-use system. It may not be usable, it may not be sustainable. It doesn't sound like it to me. Kind of like running your car on $5 a gallon gasoline. Anyway, so those are some of the interesting news items coming out. Also wanted to mention, I will be speaking this Saturday at the Central Arkansas Astronomical Society meeting, the CAAS meeting, which will be near Little Rock. And I was hoping that my friends there would get me both a web link and a physical address and exact time when I'm going to be on, and we could promote that on the show today. But that information did not reach me in time. So if we get that information, the Explore Scientific page on Facebook, I will post it there. The Astronomy for Educators page on Facebook, I will post it there. I will forward it to Scott, and he can pump it out to you. This address is going to be on astronomy education and outreach, how we can and why we must, to take a page out of Robert Zubrin's book on going to Mars. We need to do more outreach and more education. When Scott and I were young, we didn't need to have our awareness about space raised by anyone. We were putting men in orbit. We were putting men on the moon. We were sending spacecraft to Mars for the first time. It was a very dynamic time, and it was a big, big deal in the media. And so every person on Earth, quite literally, knew that space exploration was a big topic. And so astronomy as a hobby gets a big boost when we, as the general public, are aware of space science and astronomical science. All of our teachers at that time in the 1960s and 70s were teaching units and saying, "Ooh, look, we were bringing brand new television into the classroom for the first time. Wow, look, we can watch a rocket launch. We can watch a program on space exploration." And it was at the forefront of everybody's thinking. And because this was true, we didn't need anybody special doing outreach. We were all interested in astronomy anyway. Today, there's a lot more competition. You've got the little tiny screen, the fondle slab, the personal smartphone. And the interesting part about smartphones is that smartphones now, of course, groom the content that you see. If you click on an ad about, oh, look, here's a classic car. Here's something about vaccine technology. Here's something about gas prices. Here's something about the war in Ukraine. Basically, your smartphone gives you more of what you want. In the old days, a program director would pick what they thought everybody would like, and they would put together a news program. Here's stuff that will interest mom, dad, the kids, everyone. Now your smartphone does that for you individually, which means we don't all get anything. And so the question comes to us, how do we get the next great generation of astronomers interested in astronomy and space science? And that's what I'm going to be talking about with the Central Arkansas Astronomy Society. But let's go on and talk about the sad news for today. We mourn the loss of Eugene Parker, for whom the Parker Solar Probe is named. Professor Parker passed away just about a week ago on the 15th of March. He was 94. Truly a venerable gentleman and a long and productive life. God should love us all so much. But Eugene Parker, 1927 to 22, he is the only living person NASA has ever named a space mission for. And he is the only person to witness the launch of a space mission named for him. So he had a great honor in having the Parker Solar Probe named after him. Why did we name this probe after Dr. Parker? Well, in 1958, some 63 or 4 years ago, Dr. Parker predicted that there would be a solar wind. And he's not using high-tech instruments or anything else. He's just doing basic calculations with Maxwell's equations of electricity and magnetism. And he says, these charged particles should be blasted off the surface of the sun. And at the time, 1958, everybody said, no, 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 space is a vacuum. It's perfectly pristine, clean environment. There's nothing there. You could fly as fast as you want. You could stay in orbit. There's no danger except the vacuum. And he submitted this work to scientific journals, and they went, no. And what Dr. Parker did, because he was being laughed at. Oh, you're a kook, Dr. Parker. You're on the wrong track. And he appealed directly to a great physicist. And I'm probably going to massacre this name. My apologies to our folks who speak Hindi and Farsi. Subramanian Chandrasekhar, often referred to by his friends as Chandra. Chandrasekhar was a great physicist. Chandra himself had experienced this nobody believes you type of phenomenon. Starting about 1929, as a young man coming from India, he received a college scholarship to Cambridge. Wow, I'm going to England and going to the big university. And kind of as a project and going on the boat, he worked out a theory about white dwarf stars. We knew there were white dwarf stars. We didn't know what they were. We knew they were very small, very hot. Chandrasekhar said, oh, you know what? These are really dense objects. A teaspoonful would weigh millions of tons. These things are super dense and what he referred to as degenerate matter. He said, essentially, when a star dies and it collapses on itself, the only thing holding these white dwarfs up is basically the mutual repulsion of the electrons and protons. And so he basically said, yeah, these things are basically one great sphere of ultra compact matter. Then the very bizarre thing, if you add more matter to them, they get more compact. Their gravity increases and they don't get bigger, they get smaller. And a lot of people, among them Dr. Eddington, said, no, this is balderdash. Eddington had worked on white dwarf stars, and Chandrasekhar predicted that at a certain mass level, a star would die, collapse to a white dwarf. If it was bigger, he predicted, ooh, it's collapsed even farther to be essentially a giant atomic nucleus, a ball of neutrons, what we now call a neutron star. Many people opposed and said, no, this can't possibly be true. This is too outrageous. This guy is pulling our leg. And it was over 50 years. He did the initial work in 1929. He received a Nobel Prize for it, but not until 1983. And so when Parker appealed to Chandrasekhar and said, no one believes my work. Really, really, it's true. Look at the math. And Chandra went ahead and said, no, 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 we're going to publish this. And so Parker, Gene Parker, truly a man ahead of his time, predicts the solar wind. And basically, it wasn't until several years later, well, a couple of things happened. First of all, the Vanguard satellite discovers what we named the Van Allen belt. Gee, there are belts of radiation, essentially charged particles trapped in Earth's magnetosphere high above the Earth. And so space isn't perfectly clean. And then the Mariner 2 spacecraft on its way to Venus detected solar wind particles in interplanetary space. And so while all of a sudden Dr. Parker is the man who knows and the man ahead of his time, and he continued to work on these ideas until his death, working on the structure of the sun's magnetosphere, solar winds, coronal mass ejections, any number of things. And so in 2017, when NASA has this solar probe and they said, ooh, we don't like the name Solar Probe Plus, which sounds like, I don't know, a vitamin supplement or something, a tanning spray. And so they said, gee, what should we name this? And they put out a survey for the National Academy of Science, the Academy of Engineering, National Academy of Medicine. Everybody came back and said, yeah, name this after Gene Parker. He's the guy. And so NASA named the Parker Solar Probe after Dr. Eugene Parker. If you saw the little video at the beginning, there was an old gentleman with his face cocked up watching the launch. That was Gene Parker. And so let's talk about the Parker Solar Probe. Completely different than Webb. Webb takes spectra. Webb looks at light and breaks it apart into different spectra. No, Parker Solar Probe is blind in terms of what we normally consider to be electromagnetic spectra. It doesn't see visible, it doesn't see X-rays, it doesn't see gamma rays, it doesn't see infrared, ultraviolet, radio, it doesn't see any of that stuff. And it's really kind of interesting. I guess that's why they call it a solar probe instead of a solar telescope. It really doesn't focus or deal with light in any way. What it does do, it has a series of instruments. This is a large instrument. Like Webb, this too is a very big instrument. It's the size of a small bus or a delivery van. You saw some pictures of people standing around it working on the solar probe in the video Scott put on in the beginning. And this is quite a large instrument. And most of it is this very large shield. Like Webb, Parker has this tremendous shield to protect it from the energy of the sun. In the case of Webb, Webb is looking for very faint infrared signals. Any heat from the sun or even reflected from the earth would swamp its sensors. It's looking for things which are very, very low, faint signals. Parker isn't doing that, but it's simply so close to the sun that if you expose the instruments to the direct heat of the sun, they'll quickly get up to about 2,600 degrees Celsius. At that temperature, most materials melt, if not vaporize. And so Parker has to have this enormous and very powerful solar shield. And essentially its instruments kind of, peek out around the edge. There was a television show with a character who was always looking over the fence. You only saw his eyes and part of his nose. This is kind of the way Parker's instruments work. And so I thought we would take a tour of Parker's instruments, because as much as I see about the Parker Solar Probe online, I had to do some serious searching. And I'm like, okay, well, how is it doing the magic? What instruments is it using? What is it looking for? And so I did some research, and here we go. Let's take a tour, if you will, of the Parker Solar Probe. The first instrument, and yes, of course, they all have to have an acronym. The Fields instrument, and I didn't look up, sorry, I did the others. I looked up what the acronym stood for. But the Fields instrument is something that measures the electric and magnetic fields of the sun. One thing that many people don't understand about the sun, it's not a ball of fire. It's essentially a ball of plasma. Plasma, oh, we're flickering here. I'm hoping, friends, if I do disappear and you're left with Scott Headroom, the reverberating host.
Yeah. Well, the worst part of the storm is past us. Okay. So it should be okay. But yeah, if you guys lose, you know why. Okay.
Yes.
So.
Yes, it's apparently past Springdale, but we're still having power flickering. The lights just dimmed here. When we talk about the electric and magnetic field, plasma is basically atoms that are heated hot enough that the electrons boil off, they fly away, and you're left with a soup of electrons and nuclei, atomic nuclei. One's negatively charged, one's positively charged. The difference is an atom is neutral. In an atom, the positive and negative cancels out. You have as many protons as as many protons as electrons. So the charges cancel. So atoms are neutral. Atoms can be insulators. Plasma cannot. Plasma conducts electrical energy, and it also responds to magnetic energy. And so the sun, both its heat and its turbulent interior, this convective flow, creates amazingly powerful magnetic fields. And the magnetic fields stir, heat, and control the flow of the plasma. We saw that in last week's episode, how solar flares are loops of plasma that are confined by the sun's magnetic field. And sometimes the flare is powerful enough, it breaks free from the magnetic field and it blasts out into space. The field's instrument is basically measuring this magnetic and electric field that surrounds the sun, that controls its dynamics and the shape of all the eruptions and other things that happen on the surface. It uses 5 antennas, and these antennas are specially designed, very high temperature metals and materials. They're exposed to the sun directly. They reach temperatures of up to 2,500 degrees Fahrenheit. And these kind of measurements have never been made on the sun. We've never had an instrument close enough. We haven't had the technology to build antennas that would withstand the heat and radiation before. But the field's instrument does that. It's really quite astounding. And because of the way it works, it actually builds up a 3-dimensional picture of the electric and magnetic fields around the sun as the Parker probe flies in orbit. The next instrument is the WHISPER instrument. I love these acronyms, I really do. The Wide Field Imager for the Solar Probe. That's where they get WHISPER. I think they must have parties where it's like a beer pong sort of game. Who could come up with an acronym that fits for these instruments? I don't know. Maybe it's something like Scrabble or one of the game shows on TVs where they have the puzzle with the missing letters. I'm not sure. Anyway, these are 2 telescopes, if you want to call them that. And they are telescopes. They're more accurately referred to as a telescope than any other instrument on the solar probe. And they're designed to peer over and past the shield. They don't actually look at the sun directly. They're mostly focused on the corona. And there's 2 cameras. One is wide field, one is more narrow field. The interesting thing is they're going back to CMOS sensors. Now, for many decades, we've moved, I think it was in the 1990s or early 2000s, where most imaging technology moved beyond CMOS sensors to CCD sensors. The nice thing about CMOS sensors is that we can make them, design them so that they are radiation hardened. This is a kind of a technology that we talk about for satellites and for the Earth's electrical grid. Let's make it radiation hardened. And there are facilities, mostly military and government facilities, that are radiation hardened, that if there was a solar tsunami, a big coronal mass ejection event, or if there was a nuclear attack which created an electromagnetic pulse, these facilities would be radiation hardened. The radiation wouldn't destroy the electronics, wouldn't hurt the people inside. But when we come to sensors, like a standard CCD sensor, that's in the average digital camera, that's what's in your phone, that's what's in astrophotography cameras for the most part. And these CCD cameras are vulnerable to radiation. If there's a radiation surge, these imagers can be damaged, pixels can be burnt out, the whole sensor can be destroyed. And the other thing that's interesting about sensors is on all of these sensors, essentially there's the sensor in the front and then there's the electronics essentially attached right to it. And the sensors, the electronics, have been vulnerable to radiation damage as well. But with these new CMOS sensors, they're hardened against radiation, so they can be in this very high energy environment. You know, we've all heard the old joke, gee, how do you go to the sun? Well, you wait and you go at night, right? It's the old joke from the kids' big book of jokes. But seriously, when we talk about this kind of an environment, it's not just the heat. The heat is quite formidable. Thank you very much. 2,500 Fahrenheit. I don't know what that works out to in centigrade. about 15 or 1600 centigrade, but it's an alarming temperature. But the amount of radiation that you're being bombarded with that close to the sun is emitting gamma rays, X-rays, very high speed alpha particles, beta particles, all sorts of protons. And so all of these charged particles are pounding you. And these cameras are designed to peek past the worst of that and image the corona. They also use regular lenses, regular optical lenses, and they're made from specially radiation hardened BK7 glass. BK7, if you're familiar with glass technology, it's used in all sorts of optical instruments, telescopes, binoculars, for lenses, prisms, all sorts of fun things. And they're using a radiation hardened BK7 glass, which has a higher surface hardness. One of the things that they're also worried about is the impact of micro dust particles. The solar wind, not all of it is ions, some of it is cosmic dust, basically small molecules of mostly carbon, nitrogen, a few other things like that. And these molecules are moving at outrageously high speeds, tens of thousands of kilometers per hour. And this kind of a blast of these microscopically fine particles can abrade the surface of a glass lens or prism, making it worthless optically. And this specially hardened glass in the Whisper instrument is designed to withstand this harsh environment. We go on a little farther and we come to the sweep instrument. Solar wind, electrons, alphas, and protons. Sweep. And yes, it's not spelled like sweep the floor, but there you go. Now, what's interesting is this has an instrument that peers around the shield, and it's called a solar probe cup. And so what they have is a cup-shaped sensor, a collecting dish, if you will, and they have an electromagnetic field, an electric field that engulfs this cup. And they can tune the strength of this electric field. And the idea is, if you dial the electric field up very high, only the most energetic particles will be collected by the cup. And as you turn the field down, you get progressively lower and lower energy particles. So essentially, this type of a device, by sweeping the electric field strength from high to low, you can get, basically, you can map the strength, energy, and species of particles that are coming out of the sun. And it's really fascinating. You want to know what the percentage is of really high energy to mid energy to low energy? The sweep instrument can do that because it's this solar probe cup and two solar probe analyzers, span A and span B. And the solar probe analyzers are really, they're not like a telescope at all. They're a sensor for high energy particles. And these are, I'm sure our audience Scott has heard of things like an all sky camera, right? A fisheye lens that sees the whole panorama of the sky at once.
Yep.
And this is that sort of thing, except this thing sees virtually 360 degrees. It has a complete spherical view. The only place it cannot see through the solar shield. So it sees everything except the solar shield. And so it has one on the leading side and one on the trailing side. And so the two of them can track and help map these solar wind fields coming off of the sun. The next one, if you thought fields and sweep were interesting, take a look at the name of the Integrated Science Investigation of the Sun. And it looks like it's ISO with a dot in the middle and IS again. The O with the dot in the middle is the old alchemical symbol for the sun. because of course, it's not really nice to name anything after ISIS anymore, because that's a terrorist group and nobody wants to do that. My university had a parent, student, teacher portal for grades and things called ISIS. And when I got to the university in 2014, they quickly renamed that. And here again, NASA didn't want to name anything ISIS. That's an old Egyptian goddess, but there we go. So they put that symbol in there, that alchemical symbol. And if you look at the NASA webpage, they say it's pronounced like E-sis. But if you listen to the principal investigator talking about it, he says is. I don't know. It's one of those mysteries of pronunciation and language and spelling, and I guess a little bit of hieroglyphics thrown in there for fun. So there's the ISIS instrument. And this basically measures, again, electrons, protons, and other ions. Ions, remember, atoms with the electrons have been stripped away because they're too much energy. The principal ion coming out of the sun is a proton, but there's also ionized oxygen, carbon, nitrogen, helium, all sorts of ionized particles coming out of the sun. Now, the interesting thing about the ISIS instrument, like, excuse me, like the Webb solar shield, the ISIS instrument is constructed in layers. I don't know, Scott, if you've ever seen one of these cloud chambers for detecting cosmic rays.
Yes.
Right? Layered panels.
One in San Diego.
Yes, there's one. I saw one in Batavia, Illinois, at the high energy physics lab there. This is basically layers of charged material. And when a cosmic ray comes through, you see it, it makes an electric arc between each layer. And you can actually watch the path of these things. And it's quite crazy. And what they did is they made this stacked detector. So they could detect each time a particle hits a layer of foil, it kicks out electrons, and we can measure those and see them. But not only that, they took each disk of the layer and they divided it up in slices like a pie or a pizza. And each wedge is a separate detector. So a particle going through at an angle, they can not only detect its strength, its path, its direction, right? So they can sort out in their data stuff which is coming from the sun and cosmic ray particles which are coming from other directions. And this is really, it has two of these, the epi-high and epi-low energetic particle investigator for high energy. This one tracks solar flares, and this just happened. It just happened. You can look this up. This was on the news today. I didn't have time to incorporate a link in our further reading section or anything else, Scott, but we just for the first time had the Parker probe flew through a solar flare. Really quite fascinating. It flew through a solar flare, and I'm sure the people who are running this ISIS instrument are just clapping and jumping and toasting each other with flutes of champagne because this high energy particle investigator can track these extremely energetic particles. And as the little video before the show said, these particles coming off the sun, they're not moving very fast. But somehow, and we don't understand the mechanism right now, the sun's magnetic field, once they break free, they're accelerated away from the sun, reaching enormous speeds in very short order. And these investigative, the epi-high is designed to track that. The epi-low is designed to track solar wind. And the reason we have two instruments, Scott, and we see this many times, if you're trying to take a picture of the moon, there are astrophotography cameras which are not well suited. That much light would damage them. you're trying to you have to stop it down with a lot of filters. Well, when you're flying really close to the sun, you don't have the option of filters on your instrument. That's not working for you. So what they designed is this: why the ESIS has two independent instruments. One is designed and tuned for low energy stuff like the solar wind, and the other is designed for high energy blasts of radiation and particles, such as solar flares and solar prominences and different things like this. So we see that Parker is really designed. It has one camera that kind of looks at, it's not a very conventional camera, nor is it a conventional telescope, but it has one telescope. But basically, Parker Solar Probe doesn't, for the most part, deal with anything like the standard EM spectrum that we all know and love. So it's very interesting. Well, what do you do with a space probe that's blind to light for the most part? Well, what you do is you coordinate multi-resource investigations. So every time Parker is flying through the corona, and it's on its, I think, 11th orbit now, it's projected for at least 25 orbits of the sun. And it's orbiting, going out about as far as Venus and then coming back in. So this is going to take a few years. But what they do is every time Parker gets close to its perihelion, they turn all kinds of telescopes. Every telescope they have watches the sun. There's solar observatories around the world. They have Hubble look. They have the stereo A and stereo B solar imagers are working, and they have ground-based observatories, and they're all trying to image the sun. Why? Because they want to be able to coordinate what we see in visible infrared, ultraviolet, and X-rays with what Parker is seeing in primarily high energy particles. Parker is looking at, I don't know if you'd really call it a spectrum or not, but it's certainly, because most of what it sees are not rays of light or electromagnetic waves. Most of what it sees, bam, hard particles hitting sensors. And so we're getting all this great data. But again, what does it mean? We talk about when we're imaging extrasolar exoplanets, right? If we're imaging exoplanets and we're seeing this data, what does it mean? And we're looking for fast radio bursts, and we're trying to coordinate them with visible events in the sky. What does it mean? Where is it from? And can we detect by not only but by radio and X-ray, but by visible light at the same time where these things come from? And so Parker is doing the same thing. It's doing the job that no other instrument in the world can do. It's flying into these hellish environmental conditions around the sun. It's measuring the output of very high energy particles that would frankly fry and destroy virtually any other observatory, ground-based or space-based. And it's this rugged, hardened instrument designed to look at these things, but we want to be able to coordinate that with what's going on with the sun visually. And so we have the SOHO Observatory and Stereo A and Stereo B, and then all the other ground-based resources that all are interested in the sun. And so Parker becomes kind of the vanguard instrument, not just of one instrument looking at the sun, but of an entire solar observatory program that is truly global and international, with observatories around the world participating. And of course, NASA will be sharing this data with the scientific community. So it really does represent an amazing, amazing effort. So that's where we are with the solar probe. I wanted to let everybody know I got some good news from my publisher, Springer. My new book, Star Mentor, which is part of the Patrick Moore Practical Astronomy series. They've moved up the publication from June to April, which I'm very excited about. And I should be seeing galley proofs in a couple of days here to review and get back to them. And then they said the book should be available for sale come April, which is a couple of months early from what we originally were told. So that's exciting news too. And with that, I'm going to kind of take a look at the chat and see. I'm not getting many messages here. One says, if a mass coronal ejection were to occur, we have 2 or 3 days notice it's on the way. Is there anything we could do to minimize the effects? Yes, we'd like to think we have 2 to 3 days. However, coronal mass ejections travel at different speeds. The more energetic they are, the faster they get here and the less time you have to crouch in your shelter. What can you do? Yes, if we knew a gigantic solar flare was, our solar event was coming, like the Carrington event, we could put satellites in safe mode. We could go ahead and shut down our global electrical grid for an hour a day. And that would be really problematic for lots of people. As you know, there are lots of places which just don't tolerate loss of power very well. Medical facilities, research facilities, governmental facilities, military facilities. But we could, if we knew one was coming, we could take steps. What could the individual do? You know, modern cars have so many electronics in them. My wife has a 22 automobile with the amount of technology in there is just absolutely astounding. I don't know. We'd have to see if we could park in a Faraday cage, but I don't have one. That's basically a grounded metal cage. Cyclone fencing will do. So if you want to build a, wrap cyclone fencing around your carport and ground it well, that might help you. You might be the only guy driving Uber after. But I honestly don't know the answer to that. It's certainly a challenging problem that people are working on. But again, it's something that would cost trillions of dollars to design this network of protection and be able to harden our devices, et cetera, et cetera. Consider everybody on Earth would need to replace their PCs and tablets with a radiation hardened version, which would probably cost several times more than what they paid for the last one. Could you afford to do that? Don't know. Is the shape of the Parker probe affected by the solar wind? Richard Lighthill sends that. And in fact, it is not. It's a rigid structure. It's not, it kind of looks like a solar sail, doesn't it? It looks like the one end is a flex, but it's not. It's a rigid structure. And in fact, it flies and it keeps that sail. It has onboard maneuvering thrusters to keep it oriented properly. Because of course, if it goes out of orientation, things die on the probe very quickly. So alignment is critical, but no, it's a completely rigid structure. Scott, do you have any other questions or anything coming in?
Well, just a comment. Harold Block said an extreme trailer will do. My Airstream does have some electronics inside. It does, but
yes, that's right.
Would be not that would be the case. Just running.
Billie Jean, the beautiful Airstream trailer.
That's right. That's right.
Yeah, that's interesting. We could all buy Airstream trailers and ground them.
Right.
If you have a house with aluminum siding, you may be better off than those of us who do not. My house has hardy board, so it's there's no metal in it at all. Yeah, it would be a bad day. It would be a bad day. And as we
what about a basement like under the ground?
Nothing. No, because if you think about what's happening, Scott, Earth's entire magnetic field is vibrating, and a vibrating magnetic field induces current in any kind of metal. And your basement is not shielded from magnetic energy. If you take don't believe me, take your compass downstairs and it will still point north. Because the Earth is not a good shield. Think about the Earth's magnetic field penetrates through the volume of the Earth, right? So unlike radiation particles, soil, and certainly not metal are not necessarily good barriers to magnetic energy. A Faraday cage might work. Because if
quantum-
you're intercepting the
quantum that.
magnetic energy and then grounding the electrical energy produced, that might in fact work. I can see it now. There's going to be people advertising on Amazon for the EM hardening kit for your PC, which is a bunch of tin foil and a spool of copper wire.
And some
ground it.
cardboard.
Yes. Yeah, Mylar, aluminized cardboard, right? With Mylar coating.
There you go.
There you go. Don't try this at home, folks.
Don't wear it like a pyramid hat.
No, tinfoil hat will not protect you.
Right.
And really, your biological, neurological systems are not really susceptible to the kind of magnetic energy we're talking about here. So remember, we can do PET scans and things like that, and MRIs, which are basically magnetic scans of your head, and it doesn't scramble your brain. MRIs are perfectly safe for your body. So a Carrington event, and nobody died from the Carrington event. I don't know, maybe one of those fires in a telegraph office killed somebody, but you would think if animals and plants were susceptible to this kind of magnetic induction problem, there was a very big event about 10,000 years ago that would have just been a mass extinction. It didn't happen, so not to worry. That's not how you would find yourself in danger during an extreme solar event.
So probably it's not as dangerous of a situation for us here on Earth as it is for moon colonists, for example. Okay.
Yes.
That have like no atmosphere, no Van Allen belts, nothing to protect them.
There is talk about, could you, with a powerful enough device, create a personal magnetic bubble, or a magnetic bubble that would shield something the size of a bomb shelter, so you could put people inside this thing and shield yourself. Maybe no one's developed or even much less tested such a thing, but it's certainly as a science fiction writer, I would say yes, that's a possible thing, but it would take a hellacious amount of electrical energy to produce that much magnetic field to protect you. Planetary dynamos generate formidable amounts of magnetic energy. So there you go. Anyway, that's our program for this week. We're wrapping up. We're going to go on to a new topic next week. I haven't chosen it yet. I've been working on my presentation for the Central Arkansas Astronomy Society this week. I will be working and developing this week's show and sending it to Scott early, because I'm going to be busy, going to be down in Central Arkansas Friday, Saturday, and Sunday for that event. So that'll be interesting. We're hoping for clear skies and an observing night. I wish you all, our listeners and viewers all over the world, clear skies. And we'll be back next week with another exciting program. And Scott will have all his audio issues sorted by then.
It was supposed to be fixed already, so we'll see. We'll see. Thanks, guys. And looking up. And I think that's wrap, huh? Here we go.
Okay. Bye-bye, everybody.